Hi, in this video we're going to look at the topic of probability tree diagrams. This is a GCSE higher topic. If you would like any more information on this, or would like to request any questions, or you have any questions yourself, contact me on Twitter at Mr_G_Walton or our school account at Tupton Maths. Okay, in this video what we're going to do is look at being able to make a probability tree diagram from scratch, or if one's given to us with some information on, look at completing that, so looking at the information that's there and then filling in the blanks. We're going to look at being able to work out some probability outcomes by using the diagram, and we're also going to look at some tree diagrams to calculate conditional probabilities. Okay, this starts getting up to an A star topic then, so if you're able to do the conditional stuff, you want to really pat yourself on the back. Okay, so this is example 1. It says 90% of students in a school are right-handed. 18% of students in the same school wear glasses. And then it says this kind of key bit here. These statements are independent. This word independent means that one of the things does not have any reliance on the other at all. So they are not dependent on each other. So the fact that somebody's right-handed or left-handed has got no relevance at all as to whether they wear glasses or not. These things are completely independent of each other. Okay, it then says complete the tree diagram to show this information. Well, this is a really interesting one because we've got some information here on this first branch. People are either right-handed or left-handed predominantly. Now, if you both, I can see how some people might be thinking, oh, I'm ambidextrous here. It doesn't say anything about this, it just is looking in terms of right-handed or left-handed. There are only two branches, so people would have been asked, are they more left or more right? Okay, so we haven't got any other choice, it's just left-handed or right-handed. And when we've only got two things, these two branches here, they're the only two options that there are. These two branches are always going to add up to 1. Now in this case we've got 0.9 here, so we've got it as a decimal. This could equally be a fraction. Let's write that in as a fraction as well, just so we can see. That would be 9/10. And so the two branches always add up to 1. This value down here is going to be 0.1, or if you prefer we can write it as 1/10. Now, I've done it as a fraction as well because you don't know what it's going to be given as in the exam. It could be a fraction, it could be a decimal. Okay, let's look at the rest of the tree now. Over here it's talking about wearing glasses or not wearing glasses. The information up here says that 90% of the students are right-handed, and that was the 90% that we referred down here to 0.9. Now, there's another little bit of work that we need to do here. We now need to convert 18% over here to a decimal. Now, I'm hoping you can do that. 18% is 0.18. They wear glasses. And again, we can use this property of probability tree diagrams that the two branches are going to add up to 1. So in this case, if that was 0.18, this is going to have to be 0.82. And because these two statements are independent, it didn't matter whether you were right-handed or left-handed as to whether you wore glasses or not. The next two branches down here are going to be exactly the same. So 0.18 and 0.82. Now, the question doesn't ask us to do any more information than this. However, let's explore this tree a little bit more. If I wanted to know the probability of choosing one of these pupils at random, and this is key, so at random, and let's say we wanted to know the probability of them being right-handed and wearing glasses. So let's see which branch we're going to follow if we were doing right-handed and wearing glasses. Well, we're going to start looking down here. So right-handed here and wearing glasses. And I'm saying and in a particular way. And is important here. If it's something and something else, it means we're going to multiply these two things together. So if I wanted to know the probability of being right-handed and wearing glasses, and I'll put R and G for glasses, the probability of being right-handed and wearing glasses, I'm going to do 0.9 times 0.18. And I can do that either using a long multiplication method, maybe grid or something similar, or you might be asked to do this on a calculator paper, in which case you can just type it in and get an answer. In this case, we get 0.162. Now if you get an answer as you've gone down these branches, this one and this one, if you get an answer that's bigger than 1, you've made a mistake. Okay, so we know that probabilities have to be between 0 and 1. So if we've done something along here and you've got an answer bigger than 1, just check to see what's happened there. Okay, let's keep going. I'm interested to carry on doing this. Let's see what the probability of right-handed and not wearing glasses. So I'm going to put and not G, and we can use a special little bit of notation here, G dash. It just means not wearing the glasses. Let's do 0.9 multiplied by 0.82. Remember, it's this down here and this one. So we're now following a path. We've come to the right-handed. We're now choosing the different branch down here. So it was right-handed and not wearing glasses. Let's see what we've got here. I'm just doing this on my calculator, but again, you can use whatever method you prefer. Here I've got 0.738, and again I can continue to do this with the other branches too. So if I wanted to know the probability of being left-handed and wearing glasses, so the probability of left and wearing glasses, and I can also work out the last one, which was the probability of left and not wearing glasses. Let's just work these out quickly. So the probability of left and wearing glasses would be 0.1 multiplied by 0.18. That's an easy one to do. We should get 0.018 there. So 0.018. And the last one is 0.1 multiplied by 0.82, which again is fairly straightforward, 0.082. I've almost run out of space. We just rub that bit out and we'll do it again where we can fit it all on one line. So 0.082. Okay, now the reason I wanted to do this was just to show you something. It turns out that we've got this really nice property as well, that if you choose more than one of these things, if you wanted to know the probability of choosing one person, and we wanted to know the probability of them being right-handed and wearing glasses, here it is, or left-handed and not wearing glasses. Notice how we use the word or this time. So we said when we were doing and, it was multiplied. I've used the word or this time, and in this case we're going to add. If I said the probability of these two things, we can add them together. So the probability of being right-handed and wearing glasses, or the probability of being left-handed and not wearing glasses, we take these two probabilities and add them together. Now it continues to be interesting like this, because what we can say is, notice if we go along these branches, there's only 4 possible combinations we can do. We can either be right-handed and wear glasses, right-handed, not wear glasses, left-handed, wear glasses, or left-handed and not wear glasses. So if it was all these things, this one here, or this one, or this one, or this one, then if you add all these probabilities up, you get to 1. That's because there's nothing else. It's certain that it's going to be right-handed and wears glasses, or right-handed and not wears glasses, or left-handed and wears glasses, or left-handed and doesn't wear glasses. There's nothing else that it could be. Okay, I've explained on this slide a lot now about all the fundamentals of probability tree diagrams. Let's have a look in a bit more, another example, and we'll go through this fairly quickly. So this one, it says on her way to work, Yasmin goes through a set of traffic lights and over a level crossing. The probability she has to stop at the traffic lights is 0.4. The probability she has to stop at the level crossing is 0.3. These probabilities are independent. Okay, complete the tree diagram. Off we go then. So traffic lights that she has to stop, 0.4. Probability she has to stop at the level crossing, 0.3. And now I can fill in the rest. So along these two branches, it was 0.4. These two branches have to add up to 1. So here we get 0.6. This one, on the right hand side, the level crossing, if it was stopping 0.3, not stopping 0.7. Stopping 0.3, not stopping 0.7. Really nice and quick. Part B. Find the probability that on her way to work, Yasmin stops at both traffic lights and the level crossing. So it stops at the traffic lights and the crossing. Stops at traffic lights and the level crossing. So what we need to do is 0.4 and times 0.3, and that's going to give us 0.12. Okay, if you times this wrong and you get 1.2, straight away alarm bell should be ringing that I can't get a probability bigger than 1. Go back, check your working out, see what you've done wrong. Okay, these are brilliant questions because you can get a lot of marks really quickly as long as you know what you're doing. Okay, example 3, and this is one that doesn't have a tree. Here we're going to have to create it. Hasna is using a fair 6-sided spinner to play a game. She spins it twice. What's the probability she gets a 6 on exactly one of her spins? Now, at this point, what you might be thinking is, oh yeah, I'm getting good at these probability tree diagrams. Here we go, let's draw the different things out. So we could get a 1, a 2, a 3, a 4, a 5, and a 6. Oh, it's starting to get a bit unwieldy. 1, a 2, a 3, a 4, a 5. Oh, I'm starting to run out of space. That's because there is a much better way of doing it than this. All we're interested in is whether she gets a 6 or not. We have no interest in anything else. So on our first spin, why don't we say a 6 or not a 6? And on our second spin, we want to know if she gets a 6 or not a 6. 6, not a 6. Now, are they independent of each other? Does this spinner care what number you got last time? Does it make any difference to the probability? If I get a 1 on the first spin, does it make any difference as to what I get next time? Does it make any difference if I get 6 first time? I'm hoping you're answering no, Walter, it makes no difference at all. Let's just get on and get the numbers in. Okay, it's a fair-sided spinner, so the probability of me getting a 6 is going to be 1/6. I'm not even going to try and do it as a decimal. Let's just leave it as fractions. It's much easier. Remember, these two branches have to add up to 1. So 1/6 plus something is going to make 1/5. And again, we decided it made no difference at all. These are independent of each other. So I just go ahead now and write in my probabilities. And what's the probability she gets a 6 on exactly one of her spins? Right, let's see how we can do this then. If exactly 1, so that means we could get a 6, and then we don't want a 6 again because that would be 2 of her spins. So we want a 6 and this way. Okay, so this is one way that we could do it. I'm just going to highlight this a slightly different colour so we can see. So we could go this way, like this. That's an opportunity for us. Alternatively, we could go and get not a 6 first. So we could come this way. Now, if you didn't get a 6 first time, we want a 6 second time. And so it could be one or the other of these. So let's work out the maths then. So we've got a 6, so a 6 and not a 6. So a 6 times 5/6, which is 5/36. That was the first way. That was my yellow path. So that was doing a 6 and then and not a 6. And we could do it the other way. We could also do 5/6 multiplied by 1/6, which is exactly the same. I get another 5/36. Now, it's much easier when you're doing probability to not cancel down. Typically in these questions, you'll be in fraction questions, you always look and see if you can cancel down. Now this time it doesn't, but even if it did, I'd say don't until right at the very end if you really must do. Typically GCSE questions don't ask you to cancel your probabilities down, so you don't have to worry. Let's just have a think about what we need to do now. The last thing it said, it was exactly one of our spins. It could be this root or this root. Remember, or means add, so I can add these two fractions together. The denominators are the same, brilliant. So all we've got to do is add the tops, which means that my final answer is going to be 10 over 36, which if you really want to, you can cancel down to 5 over 18. So 5/18. But like I say, GCSE questions, typically you're not asked to cancel them down. You can just leave it as 10 over 36 and be happy. Okay, last example then. This time I want to have a look at an example when the first thing does depend on the second. So these are not independent. In fact, they are dependent or conditional. Okay, let's read the question. It says that Anne drives to work. She estimates that in November it rains on 1 morning out of 3. She also estimates that if it's raining, the probability she'll be delayed is 3/5. If it's not raining, the probability she'll be delayed is 1/5. Use the tree diagram to calculate the probability that on 1 November morning Anne will be delayed. Okay, so let's fill in some information then. So what have we got so far? Well, we know that it's raining 1 morning out of 3. Okay, so this is a third. And that means it must be not raining on the other 2 days out of 3. So a third and 2/3. If it's raining, so now I'm interested in this branch. If I've come along here and it's raining, what's the probability that she will be delayed? Well, it's 3/5. It tells us that in the question. Remembering our facts about our tree diagrams, the branches here have to add up to 1. So that means that this must be 2/5 here. And continuing along here, let's have a look. Now, in the past, whenever we've done these, we've just copied this information straight down here. We can't do that this time because something has happened. There's something that's different. It says if it's not raining, the probability should be delayed is 1/5. This is very similar to questions that you might have seen in class where somebody takes a sweet from a bag and eats it. They don't replace it, which means that the next time you put your hand in the bag, there's going to be one less of those sweets. And so it depends on the sweet that you've taken out, but you know there's one less, and it depends on which one you've eaten, which branch you've gone down as to which one. Okay, so it's similar to one of those. Let's see what it says. If it's not raining, the probability should be delayed is only 1/5. So this is 1/5 here, which means down here we're going to get 4/5. Okay, let's go ahead and work out what the question's asking us to do. It says what's the probability that she will be delayed. So that means that we could go this way. This is a delayed. I'm interested in this branch. And also, there's another way of being delayed here. So it's one or the other. Let's multiply these two things. So working along the branches, I've got a third multiplied by 3/5, which is going to give me 3/15 along this branch. Or down here, 2/3 multiplied by 1/5. Remember, I'm multiplying because I'm travelling down the branches like this, one and the other. So I've got 2 over 15 here. And the question is, it could be this one here or this one. So I need to add these two things together and I get a final answer of 5/15, which cancels down to a third. This is one for you to have a go at yourself. I'm going to read the question out. I'm going to give you a little bit of information before I pause it, and then I want you to have a go yourself. So it says the probability of randomly choosing an ace from a pack of 52 playing cards is 1 out of 13. Colin chooses a card at random from the pack, and then chooses another card at random. Calculate the probability that Colin chooses 2 aces. Now, Colin's picked up a card, he's kept it in his hand. He's not put it back in the deck. So next time he pulls one out, you need to be really confident and careful about how many cards are now in the deck. Bear in mind he's got one in his hand. And you don't know what that one in his hand is. It could be an ace, or it might not be. Pause the video, have a go and let's see if we can compare our answers. Okay, so I gave you a few clues a second ago. What I said was that we've got this kind of situation here where the probability is going to get an ace or not an ace. This is what we're interested in. So the probability he picks an ace first time is 1 out of 13. That means the probability he doesn't get one is 12 out of 13. Now the next time he pulls a card randomly from this pack, one of the cards is missing. So if he had an ace, if he picked an ace first time, then we're interested in an ace the second time, or not an ace. Now I could continue down this branch as well with an ace and not an ace. However, I don't think it's going to help us because all we're interested in is the probability that he chooses two aces. So if he's taken one of these cards out, then there are now only 51 cards left. And how many aces are there if he's already picked one of the aces out here? Well, there were 4 to start with. We should know that there are 4 aces in a pack of cards, so that means there's only 3 left now. So the final thing we need to do is multiply along here. So we've got 1/13 multiplied by 3 over 51, which is going to give me 3 over. Now again, you can use whatever method you like to multiply these. I've used my calculator because I'm being lazy today. But I've got 3 over 663. Now again, I'm looking at these numbers. I've spotted that they cancel down. This will cancel down to 1 over 2, 2, 1. The probability of choosing 2 aces, one first, keeping it, and a second one, is 1 out of 221. It's not impossible, but it's unlikely. Okay, finally, here is a chance for you to make some revision card notes. What I would say is make sure that you're confident about using these tree diagrams. Draw yourself a little one to show what the different things could happen are. You might want to annotate it to say that you multiply along the branches and that you add the different combinations down here. So we do, if it's one or the other, you add them, and along here we're saying and. And in particular, what I'd be thinking about is that the 2 things along the branches, so let's call this A and let's call this B, so that whether they're decimals or fractions, or they could even be percentages, we know that these 2 things, A and B, have got to add up to 1 whole 1. What else do we know? Oh, we also need to think about what's happening on the right hand side. Does that depend on what's happened before? So does this depend on that? Just like we saw in the last 2 questions, it did. Sometimes we're given some information. Sometimes we have to use our noggin a little bit and have a really good think about what's happening. Try and pretend you're doing it in your head. I know you might feel a little bit silly, but it's a really good way of doing it. And be really careful what it is that you're writing on the probability tree diagrams here. Try and keep it neat and tidy. Ideally, you don't want any more than 3 branches. Okay, so if there's questions about rolling a dice, think, do I really need to put all 6 branches, or can I get away with just 2? Okay, hopefully this has been useful for you. As ever, I wish you all the very best of luck in any exams that you've got coming up or in the future. And if you need anything, get in touch. Bye.